Unit 2. Now we are going to see the definition of Lagrangian. Let pi1 of t, pi2 of t, etc. pi n of t be real or complex valued function defined on the interval I and each having derivatives of order n. For t belongs to I, we define the determinant w of t equal to w of pi1, pi2, etc. pi n of t. That is equal to, we write this determinant. In the determinant, in the first row, we write all the functions pi1 of t, pi2 of t, etc. pi n of t. In second row, for all these functions, we calculate first derivatives. Pi1 dash of t, pi2 dash of t, and etc. pi n dash of t. In third row, we find second derivatives. Pi1 double dash of t, pi2 double dash of t, etc. pi n double dash of t. So this will be going on, and etc. In the last row, we find n minus 1th derivative for pi1, pi2, pi3. Therefore, the last row elements are n minus 1th derivative of pi1, n minus 1th derivative of pi2, n minus 1th derivative of pi n. So this is the definition of Lagrangian. So based on this definition, now we are going to see the problem number 1. Find the Lagrangian WD of function e power t, cos t, sin t. First, we take these functions as pi1 of t, pi2 of t, pi3 of t. So pi1 of t equal to e power t, pi2 of t equal to cos t, and pi3 of t equal to sin t. Now we are going to apply the definition of Lagrangian, that is w of t equal to, in first row we write all these functions e power t, cos t, sin t. In the second row, corresponding to these functions, we calculate the first derivatives. First derivative, that is e power t. When you differentiate cos t, we get minus sin t. When you differentiate sin t, we get a cos t. In third row, we calculate second derivative for pi1, pi2, pi3. So if we differentiate e power t, we get e power t. If we differentiate minus sin t, we get minus cos t. If we differentiate cos t, we get minus sin t. So this is w of t. Now we have to expand this determinant. So in this determinant, we can take out the common element in the first column, and that is e power t. So e power t into here 1 cos t sin t, 1 minus sin t cos t, then 1 minus cos t minus sin t. Right. To expand this determinant, we can simplify this using elementary row operations. So if you simplify this determinant, we can easily expand. Therefore, we can apply the elementary row operations. Here we write R1 plus R3 goes to R1. That means the two rows R1 and R3 can be added, and the resultant value should be written in the row R1. So this is the row operation. According to this row operation, we perform this. So there is only change in R1. In R2, R3, there is no change. So we get 2, 0, 0. Here 1 minus sin t cos t, 1 minus cos t minus sin t. So in this determinant, there are two zeros. Therefore, it is very convenient form to expand this determinant very easily. So when you expand this determinant, we get 2 into e power t into sin square t plus cos square t when you expand this. So sin square t plus cos square t, that is 1. Therefore, w of t equal to 2 into e power t. Similarly, we can do the next problem. Find the Lagrangian w of t of the functions e power t, e power minus t, e power it, e power minus it. Now we write the solution. We take all these functions as pi1, pi2, pi3, pi4. Now we calculate the Lagrangian, that is w of t equal to the determinant. Then in the first row, we write all these functions here. In second row, we calculate first derivative. In third row, we calculate second derivative. In fourth row, we calculate third derivative. So all derivatives are calculated in this determinant. Now we can expand this. In this determinant, we can take out the common element in each column. So in first column, we can take out e power t as the common element. In the second column, we can take it out e power minus t as the common element. In third column, we can take it out e power it as the common element. In fourth column, we can take it out e power minus it as the common element. So after taking all the common elements, the remaining determinant can be written like this. When you multiply these values, then this will be reduced to e power 0, that is e power 0 is 1. So next we have to expand only this 4 cross 4 determinant. Here we simplify this determinant using elementary row operations. So here we have 2 zeros in this determinant. Now again we apply the operation C2 goes to C1 minus C2. Then this determinant can be reduced to 3 cross 3 determinant. So this is convenient form where we can expand the determinant very easily. Again, if you apply the elementary row operation, R1 goes to R1 plus R3. This can be further simplified with the 2 zeros. Therefore, this is the very convenient form to expand the determinant. So when you simplify this, minus 2 into 4 into minus I, that is minus 8 into minus 2i, that is equal to 16i. So this completes the problem. Next, differential equations with the variable coefficients. Let us consider a differential equation of order n with the variable coefficients in the following form. A0 of t into x power n plus a1 of t into x power n minus 1 plus a2 of t into x power n minus 2, etc. an of t into x, that is equal to h1 of t. This can be taken as equation number 1, where a0, a1, a2, etc. an are real or complex valued functions defined on the interval I of the real line R. We assume that a0 of t not equal to 0. Divide both sides by a0 of t on a0 of t. Then we get this result. Then when you simplify this, finally this is reduced to this equation. Here we take bi equal to ai by a0 and h of t equal to h1 of t by a0 of t. Therefore, Lx of t equal to x power n plus b1 of t into x power n minus 1 plus b2 of t into x power n minus 2 plus etc. bn of t into x equal to h of t. Here, L denotes the operator on a function x with the differentiation n times on the interval I. So, in case h of t equal to 0 for t belongs to I, then L of x of t equal to x power n of t plus b1 of t into x power n minus 1 plus b2 of t into x power n minus 2 plus etc. plus bn of t into x of t equal to 0 where t belongs to I. So this is a linear homogeneous differential equation. In case h of t not equal to 0 for t belongs to I, then we have L of x of t equal to h of t is a linear non-homogeneous differential equation. To find the solution of the differential equation, we need n conditions, initial value problem for nth order differential equations. L of x of t equal to h of t, comma t belongs to I. With the initial condition x of t naught equal to alpha naught, x dash of t naught equal to alpha 1, x double dash of t naught equal to alpha 2, x triple dash of t naught equal to alpha 3, etc. X n minus 1 dash of t naught equal to alpha n minus 1, where alpha naught, alpha 1, alpha 2, etc. alpha n minus 1 are constants, where t belongs to I. Next theorem. So theorem without proof. Let b1, b2, b3, etc. bn be the constant function on the interval I, which contains a point t naught. Let alpha naught, alpha 1, alpha 2, etc. alpha n minus 1 be any n constants. There exists a unique solution phi on I of nth order differential equation x power n plus b1 of t into x power n minus 1 plus b2 of t into x power n minus 2 plus etc. bn of t into x equal to 0, where t is a point in the interval I, satisfying the initial conditions phi of t naught equal to alpha naught, phi dash of t naught equal to alpha 1, phi double dash of t naught equal to alpha 2, etc. This will be going on. So phi n minus 1 dash of t naught equal to alpha n minus 1. Right. So using this theorem, now we are going to do some problems. Problem number 1. Prove that there are 3 linearly independent solutions in third order equation x triple dash plus b1 of t into x double dash plus b2 of t into x dash plus b3 of t into x equal to 0, where t is a point in the interval I. Now we write the solution. Consider the differential equation x triple dash plus b1 of t into x double dash plus b2 of t into x dash plus b3 of t plus x. So b3 of t into x equal to 0, where t is a point in the interval I, where b1 of t, b2 of t, b3 of t are constant functions defined on the interval I. Here phi 1, phi 2, phi 3 are 3 solutions of third order differential equation. So applying the above theorem, here we use these initial we use these values. Phi 1 of t naught equal to 1, phi 1 dash of t naught equal to 0, phi 1 double dash of t naught equal to 0, phi 2 of t naught equal to 0, phi 2 dash of t naught equal to 0, phi 2 double dash of t naught equal to 0. Then phi 3 of t naught equal to 0, phi 3 dash of t naught equal to 0, and phi 3 double dash of t naught equal to 1. So this will be an initial data. So now we take the linear combinations. Let us C1 into phi 1 of t plus C2 into phi 2 of t plus C3 into phi 3 of t equal to 0. And next C1 into phi 1 dash of t plus C2 into phi 2 dash of t plus C3 into phi 3 dash of t equal to 0. The next C1 into phi 1 double dash of t plus C2 into phi 2 double dash of t plus C3 into phi 3 double dash of t equal to 0. At t equal to t naught, we have these equations. C1 into phi 1 of t naught plus C2 into phi 2 of t naught plus C3 into phi 3 of t naught equal to 0. Similarly, we get other two equations. Applying the initial data that we have given here. So using these initial data values, we can get this. Here C1 into phi 1 of t. What is phi 1 of t? Phi 1 of t is 1. So we can substitute C1 into 1. Similarly, we can apply all these values in this equation now. That is C1 into 1, C2 into 0 plus C3 into 0. So this can be represented like an a unit matrix form: 1 0 0 0 1 0 0 0 1. This can be taken from the initial data that we have prescribed. 1, 0, 0, 0, 1, 0, 0, 0, 1. So when you apply this initial data, we get the three equations 1, 2, 3. From these three equations, we get C1 equal to 0, C2 equal to 0, and C3 equal to 0. Therefore, all constant values are 0. Therefore, the functions pi1 of t, pi2 of t, and pi3 of t are linearly independent solutions of given third order differential equation. This idea can be extended for nth order differential equation. That means we prove the same for nth order differential equation in the following manner. Prove that there are n linearly independent solutions in nth order differential equation. We follow the same logic for nth order differential equation. Next theorem. Let pi be any solution of the equation, third order equation, the differential equation x double dash plus b1 of t into x double dash plus b2 of t into x dash plus b3 of t into x equal to 0 existing on interval I. Further, let pi1, pi2, pi3 be three linearly independent solutions. Show that there exist constants C1, C2, and C3 such that pi equal to C1 into pi1 plus C2 into pi2 plus C3 into pi3. Now we write the proof. This proof is based on the previous theorem without proof. So this is the theorem without proof. This statement can be applied. So now we write the proof for this theorem. Since pi is a given solution of this third order differential equation x double dash plus b1 of t into x double dash plus b2 of t into x dash plus b3 of t into x equal to 0. At t equal to t naught, there exists constants alpha 1, alpha 2, alpha 3 such that pi of t naught equal to alpha 1, pi dash of t naught equal to alpha 2, pi double dash of t naught equal to alpha 3. The solutions pi 1, pi 2, pi 3 are given as given in the above problem. Define a function psi on the interval I such that psi of t equal to alpha 1 into pi 1 of t plus alpha 2 into pi 2 of t plus alpha 3 into pi 3 of t. Here psi of t satisfies the equation x double dash plus b1 of t into x double dash plus b2 of t into x dash plus b3 of t into x equal to 0. Here psi of t naught equal to alpha 1, psi dash of t naught equal to alpha 2, psi double dash of t naught equal to alpha 3. Thus we have two solutions pi of t and psi of t having the same initial conditions. Therefore, from the above theorem, pi of t equal to psi of t. So this completes the proof. So this result can be extended for nth order differential equation. So combining the above two results, we can prove the following theorem. Theorem 5. Theorem 5. There exists n linearly independent solutions of the interval on the interval I of nth order differential equation x power n of t plus b1 of t into x power n minus 1 of t plus b2 of t into x power n minus 4 of t plus etc. b1 of t into x of t equal to 0, where t is a point in the interval I. If pi 1, pi 2, pi 3, etc., pi n are linearly independent solutions of linearly independent solutions, and Phi is any other solution of nth order equation existing on the interval I. Then there exist n constants C1, C2, etc. Cn such that phi equal to C1 into pi 1 plus C2 into pi 2, etc. Cn into pi n, where t is a point in the interval I. Now we write the proof. Consider the differential equation x power n plus b1 of t into x power n minus 1 plus b2 of t into x n minus 2 of t plus bn of t into x of t equal to 0, where b1 of t, b2 of t, etc. bn of t are constants function defined on the interval I. Here pi 1, pi 2, pi 3, etc. pi n are the solutions of the nth order differential equation. Applying the above theorem, here we put the initial data like a unit matrix form for nth order differential equations. Here we need a n functions. Here pi 1 of t naught equal to 1, pi 1 dash of t naught equal to 0, pi 1 double dash of t naught equal to 0, etc. pi 1 n minus 1 dash of t naught equal to 0. In second row, pi 2 of t naught equal to 0, pi 2 dash of t naught equal to 1, pi 2 double dash of t naught equal to 0, pi 2 n minus 1 dash of t naught equal to 0. So proceeding similarly, we come to the last row, that is pi n of t naught equal to 0, pi n dash of t naught equal to 0, pi n double dash of t naught equal to 0. The last element, that is pi n n minus 1 dash of t naught equal to 1. So this will be the data is given like a unit matrix form. Now we take the linear combination. Let us C1 pi 1 plus C2 pi 2 C3 pi 3 etc. Cn pi n equal to 0. Now we get the first differentiation in the second row, second differentiation in the third row, the last row we get n minus 1 the differentiation. So we obtain these equations. At t equal to t naught, we have these equations. Applying the above data given in the unit matrix form, applying the initial data, we get here C1 into 1 plus C2 into 0, all other values are 0. C1 into 0 plus C2 into 1 plus all other values are multiplied by 0. Similarly, we put all the values like this. The finally we write C1 into 0, C2 into 0, last one Cn into 1 equal to 0. So there are several equations. So in this, all constant values are 0. C1 equal to 0, C2 equal to 0, C3 equal to 0, Cn equal to 0. Therefore, all the functions pi 1, pi 2, pi 3, etc. pi n are linearly independent solutions of given nth order differential equation. Since pi is a given solution of this nth order differential equation, at t equal to t naught, there exists constants alpha 1, alpha 2, etc. alpha n such that pi of t naught equal to alpha 1, pi dash of t naught equal to alpha 2, pi double dash of t naught equal to alpha 3, etc. pi n minus 1 dash of t naught equal to alpha n. The solutions pi 1, pi 2, pi 3, etc. pi n are given in the above theorem. A function psi on the interval I such that psi of t equal to alpha 1 pi 1 plus alpha 2 pi 2 etc. alpha n pi n. Here psi of t satisfies the equation x power n of t plus b1 of t into x power n minus 1 of t plus etc. plus bn of t into x of t equal to 0, where t is a point in the interval I. Here psi of t naught equal to alpha 1, psi dash of t naught equal to alpha 2, psi double dash of t naught equal to alpha 3, etc. Psi n minus 1 dash of t naught equal to alpha n. Thus, we have n solutions pi of t and psi of t having the same initial conditions. Therefore, from the above theorem, pi of t equal to psi of t. So, this completes the theorem. Now, we are going to do problem number 1. solve y double dash minus 2y dash plus y equal to 0 and y of 2 equal to 1 and y dash of 2 equal to minus 2. The y double dash means this is y double dash of t. Y dash, that is y dash of t. So y means y of t. So the given equation can be written as y double dash minus 2y dash plus y equal to 0. The characteristic equation is p of lambda is equal to lambda square minus 2 lambda plus 1 equal to 0. If you solve this equation by factorization method, we get lambda minus 1 into lambda minus 1 equal to 0. Therefore, lambda equal to 1, 1 are repeated roots. Therefore, y of t equal to, the solution is y of t equal to c1 plus c2 into t into e power t. This can be taken as equation number 1. So we are given that the initial values are given in the problem itself. So we are given that y of 2 equal to 1, y dash of 2 equal to minus 2. So from y of t we calculate y dash of t. Y dash of t equal to, we get this result, this equation number 2. So we are given that y of 2 equal to 1. So using this relation we get c1 plus 2c2 equal to e power minus 2, that is equation number 3. So the another initial condition, y dash of 2 equal to minus 2. So using this we get another equation, c1 plus 3c2 equal to minus 2 into e power minus 2. This is equation number 4. Solving equations 3 and 4, we get values for c1 and c2. That is c2 equal to minus 3 into e power minus 2 and c1 equal to 7 into e power minus 2. Therefore, the c1 and c2 values are substituted in y of t. Therefore, y of t is equal to 7 into e power minus t minus 3 into e power minus t. So the c1, c2 values are substituted in the solution. Therefore, this is the solution of the given initial value problem. So here c1 and c2 values are substituted. So finally here we write e power t. So here this is a c1 value and this is c2 value. The c1 and c2 values are substituted in this solution equation 1, that is y of t equal to c1 plus c2 into t into e power t. So this completes the problem. Next problem, solve y triple dash minus y equal to 0, y of 0 equal to 3, y dash of 0 equal to 1, y double dash of 0 equal to 1. Now we write the solution. The given equation is y triple dash minus y equal to 0. Now we write the characteristics equation is p of lambda is equal to lambda cube minus 1. So when you solve this equation, we have 3 roots. The 3 roots can be obtained by using the synthetic division method. So we write this equation in order with the corresponding coefficients. Lambda cube minus 1 can be written as lambda cube plus 0 lambda square plus 0 lambda minus 1. So put these coefficients in for this synthetic division. So by trial and error method, we divide by 1. So when you divide it by 1, the remainder is 0. Therefore, lambda minus 1 is a factor. So the given equation can be written as, so lambda cube minus 1 can be written as lambda minus 1 into lambda square plus lambda plus 1. So these coefficients 1, 1, 1 can be used to for forming the quadratic equation lambda square plus lambda plus 1 equal to 0. When you solve this quadratic equation using the formula, we get lambda equal to minus 1 by 2 plus or minus root 3 by 2 into I. Here alpha is minus 1 by 2, beta is root 3 by 2. Therefore, the general solution is y of t equal to c1 into e power t plus e power minus 1 by 2 into t, e power minus 1 by 2 into t into c2 cos root 3 by 2 into t plus c3 sin root 3 by 2 into t. Now we find the constant values c1, c2 and c3 using the initial conditions y of 0 equal to 3, y dash of 0 equal to -1, y double dash of 0 equal to 1. Now we calculate y dash of t. So this is equation 1 is y of t. Now we calculate y dash of t. So this is y dash of t. For y dash of t, again we calculate y double dash of t. So this is y dash of t, and this is y double dash of t. So in these equations, we use the initial conditions. We are given that y dash of 0 equal to 1. Using this, we get the equation C1 minus 1 by 2 into C2 plus root 3 by 2 into C3 equal to -1. Then this is the equation for y double dash of t. In this, we use the initial condition. Y double dash of 0 is equal to, we get, that is 1. Then we get the equation 2. Here y of 0 equal to 3. So using the solution y of t, we find y of 0 equal to 3. So here we get C1 plus C2 equal to 3. This is equation number 3. So solving these equations to find the values of C1, C2, C3. So 1 minus 2 implies we get C3 equal to -2 by root 3. When you simplify these two equations, we get 2C1 minus C2 equal to 0. We get this equation 2C1 minus C2 equal to 0. This is equation number 4. So solving the equation 3 and 4, we get this result. In this, we calculate 3C1 equal to 3. Therefore, C1 equal to 1. So this can be applied in this equation. That is C1 plus C2 equal to 3. From this, we find a C2. So C2 is 2. So we have obtained all the three constants C1, C2, C3. So that will complete the problem. Right. Next, theorem. This is Varankson theorem. The statement is, let the B1, B2, B3, etc. Bn be a real or complex valued functions defined and continuous on an interval I, and pi1, pi2, pi3, etc. Pi n are n solutions of the equation x power n of t plus b1 of t into x power n minus 1 of t plus b2 of t into x power n minus 2 of t plus etc. bn of t into x of t equal to 0, where t is a point in the interval existing on I. These n solutions are linearly independent if and only if Varankson of t not equal to 0. Now we write the proof. The proof consists of two parts. First, we assume that the solutions are. First, we assume that there are n constants C1, C2, etc. Cn such that the linear combination gives 0. Then we prove that pi1, pi2, pi3, pi n are linearly independent. That is first part. Second part, we assume that pi1, pi2, pi3, pi n are linearly independent. Then prove that there exist n constants C1, C2, C3, etc. Cn such that this linear combination gives a 0. So now we are going to see the proof. Let there be a point T1 in the interval I such that Varankson of T1 not equal to 0. Assume that there are n constants C1, C2, C3, etc. Cn such that C1 pi 1 plus C2 pi 2 plus etc. Cn pi n equal to 0. Claim. So here we prove that all the functions pi 1, pi 2, pi 3 are linearly independent. That means we are in the linear combination. We prove all the constant values are 0. That is to prove C1 equal to 0, C2 equal to 0, etc. Cn equal to 0. At t equal to T1, we have these equations. That is C1 pi 1 of T1 plus C2 pi 2 of T1, etc. Cn pi 1 of T1 equal to 0. Here so we get the similar equations. Then we use the following initial data that we have applied this concept in the previous problems. That is, the data values are given like an unit matrix form. So they are to be supplied here. So this initial data can be applied in the following linear equations. These are n simultaneous equations in C1, C2, C3, etc. Cn as unknown terms. We see that the determinant found by the coefficient of the n equation is n equations in W of T1 not equal to 0. Here we apply the initial data that is given in the unit matrix form C1 into 1. All other values are 0. In second equation, C1 into 0 plus C2 into 1 and all other values are 0. Similarly, the last one, here all these values are 0 here except the last one, Cn into 1 equal to 0. So in this linear combination, we see that all the constant values are 0. So C1 equal to 0, C2 equal to 0, Cn equal to 0. Therefore, the functions pi 1, pi 2, etc. pi n are linearly independent. Thus, overfunction of t not equal to 0 is necessary to obtain a sufficient condition. Right. So from this, we say that if pi 1, pi 2, pi 3, pi n are linearly independent, then we say that overfunction of t not equal to 0. Similarly, if overfunction of t not equal to 0, then we say that pi 1, pi 2, pi 3, pi n are linearly independent functions. Right. Then second part, assume that pi 1, pi 2, pi 3, pi n are linearly independent solutions on the interval I. Claim overfunction of t not equal to 0 for some t1 belongs to I. Some t belongs to I. Suppose overfunction of t1 equal to 0 for some t1 belongs to I. Then we will arrive at a contradiction. Now we are going to see that contradiction. Let us consider some system of equation. Some system of equations C1, C2, etc. Cn. Since overfunction of T1 is equal to 0, the system has solutions C1, C2, C3, Cn. All of them need not be simultaneously 0. So with these values of C1, C2, C3, etc. Cn, we can find a function pi such that pi of t equal to C1 pi 1 plus C2 pi 2, etc. Cn pi n. Clearly, pi of t is also a solution of given nth order differential equation with a variable coefficient. Further, it should be the initial conditions. So pi of t1 equal to 0, pi dash of t1 equal to 0, pi double dash of t1 equal to 0, etc. Pi n minus 1 dash of t1 equal to 0. So this implies pi of t equal to 0 in the interval I. So this implies this linear combination gives 0 where C1, C2, C3, Cn are not simultaneously 0. So this implies the solutions pi 1, pi 2, pi 3 are linearly dependent on the interval I. So which is a contradiction to the assumption. Therefore, overfunction of t not equal to 0 for all t in the interval I. So this completes the proof of the overfunction theorem. Right. Next one, Abel's formula. So state and prove Abel's formula. So here first we write the statement. Let the functions b1, b2, etc., b3, etc., b and in equation xn of t plus b1 of t into x power n minus 1 of t plus b2 of t into x power n minus 2 of t, etc., plus bn of t into x of t equal to 0. We defined and continuous on an interval I. Let pi 1, pi 2, pi 3, etc., pi n be n linearly independent solutions existing on the interval I containing a point t0. Then variation of t equal to e power minus interval t0 to t1 v1 of s into ds into variation of t0. So we have to prove this result. So write the proof. So variation of t. So this is the definition for variation. In this definition, first row we write the functions. We write all the functions as it is. Second row we calculate first derivative. Third row we calculate second derivative. In the last row we calculate n minus 1th derivative. So this is the definition of variation. So now we are going to differentiate this determinant w of t. So differentiating this with respect to t, we get a w dash of t. So now we are going to see the procedure how to differentiate a determinant. When you differentiate this determinant w of t, we get a w dash of t, that is equal to here in this determinant. So w dash of t is equal to the sum of all these determinants. Here in the first determinant we differentiate first row functions only. All other rows we keep as it is. Plus in second determinant we differentiate only the second row. We keep all other rows as it is. In plus in third determinant we differentiate only third row of functions. We keep all other rows as it is. Plus etc. Plus in the last determinant we differentiate only the last row functions. In all other rows we keep the elements as it is. So while doing this process, we differentiate elements in each row, keeping other rows fixed in the process. Since there are n rows in the determinant, that is the derivative w dash of t turns out to be the sum of n determinants of which the first n minus 1 determinants are 0. Since each of them has two identical rows, so only the last determinant has all rows distinct. Here in finding these derivatives, you see in the first determinant two rows are identical. In the second determinant the another two rows are identical. Similarly, in third determinant, here another two rows are identical. Only in the last determinant, all rows are distinct. Therefore, in this, all determinant values are 0 except the last determinant. Because except the last determinant, all other determinants are having identical rows. Therefore, those determinant values are 0. Right. Since pi 1, pi 2, pi 3, etc., pi n are solutions of xn of t plus b1 of t into xn minus 1 of t plus bn of t into x of t equal to 0, L of pi I equal to pi I power n. So instead of x we put pi I. So pi I power n plus b1 into pi I power n minus 1 plus b2 into pi I power n minus 1 etc. plus bn pi I equal to 0. Here pi I power n can be written as minus b1 into pi I power n minus 1 minus b2 into pi I power n minus 2 etc. minus bn into pi I. This can be taken as equation number 1. Here you see pi1 power n equal to minus b1 into pi1 power n minus 1. Pi2 power n is equal to minus b1 into pi2 power n minus. Similarly, pi3 power n, I will when you see that the first element will be minus b1. Here minus b1, here minus b1. In the next term also the first term should be minus b1. So now we see that last row of the last determinant contains the terms pi1 power n, pi2 power n, pi n power n. So which can be replaced by the above relation 1. The right side of equation 1 is the sum of functions pi power n, so the right side of 1 is the sum of functions pi I power 1, pi I power 2, pi I power n minus 1 with some multiplies. Now we see that these functions also appear in the upper rows. By using the usual operations in the determinant, we have a w dash of t equal to, here we write down, here you see the last row. In the last row, first in every function, the first value will be minus b1, minus b1, minus b1. Here, so minus b1 will be the common element. And now we can take it out. So minus b1 into, we write the remaining expressions. So this will be nothing but the definition of Lorentzian. Therefore, w dash of t equal to minus b1 into w of t. This can be written like this: w dash of t plus b1 into w of t equal to 0. This can be written as dw by dt plus b1 into w equal to 0. By this can be written as dw by dt equal to minus b1 into w. By variable separable method, we can integrate this. We get log w equal to minus b1 into dt plus c. Therefore, w is equal to e power so e power in minus integral b1 of b1 in dt plus c. So this can be written as w is equal to e power minus integral t naught to t b1 of s into ds. So this can be written as e power minus integral t naught to t b1 of s into ds into w of t naught. This is a constant value, where w of t naught is equal to e power c. Therefore, w of t equal to e power minus integral t naught to t b1 of s into ds into Lorentzian of t naught, where t belongs to I. So this completes Abel's formula.